Section 5.3 has a whole bunch of other proofs that show examples of how to do proof by induction. The first group deal with doing divisibility properties. And if you read over the section on divisibility and look at the sample proof that's on page 260, that might be helpful. I am not going to hold you to being able to do the problems with the inequalities or the problems dealing with trinominos instead of dominoes. They're kind of fun puzzles, but they're not going to be really useful for you going ahead in computer science. So that you have a good example of how to do this in a way that would match up with problem 4 on the Proofs 2 worksheet. I'm going to do problem number 8 from the text in this section, and we're going to go through it. What problem number 8 says is that 5 to the n minus 1 is divisible by 4 for each integer n greater than or equal to 0. And I've written that here with our symbols. Our base case for this, of course, is when n is 0. So what we need to do is we need to show that 4 divides 5 to the 0 minus 1. Now, what does 5 to the 0 minus 1 mean? Well, 5 to the 0 is 1 minus 1, and 1 minus 1 is 0. So what we're needing to show is that 4 divides 0. 4 divides 0 because 0 is equal to 4 times 0. That's using the definition of divides. So we have completed the base case. Now let's move on to the inductive case. For our inductive case, what we need to do is to assume that this statement is true for the kth case. In other words, for when n is equal to k. In other words, 4 divides 5 to the k minus 1. We need to show that it's then true for the next case, p of k plus 1. In other words, when n is equal to k plus 1. In this example, 4 divides 5 to the exponent of k plus 1 minus 1. Now this particular proof is just a little different from the ones we've done before, but it still follows the basic idea of doing an induction proof. What we're going to do is we're going to start with what we're assuming. We're going to assume that 4 divides 5 to the k minus 1. Now, by the definition of divides, what does this mean? It means there exists some integer, let's call it x, where 5 to the k minus 1, the right-hand side here, is equal to 4 times x. Okay, now it's kind of hard to tell where to go from there, but it might help if we think about where we're headed in the long run. We're trying to get to the result that 4 divides 5 to the k plus 1 minus 1. If we use that same definition, okay, let's work backwards and use the definition of divides down here, we can see that that would say there exists some other integer y, which is y is an element of z. We can see that 5 to the k plus 1 minus 1 is going to be equal to 4y. So what this means is we have to somehow turn this expression we have here into this expression. Well, there's a little trick you can use to, I think, make this easier, and that's to write the part with the exponents all by itself on the left-hand side. Let's rewrite this as 5k is equal to 4x plus 1. And we could do the same thing down here at the bottom. You could see that 5 to the k plus 1 is going to equal 4y minus 1. So somehow we need to turn this into this. Let's concentrate just on the left-hand side at first. How are we going to change 5 to the k, meaning we have k factors of 5, into 5 to the k plus 1, meaning we have one more factor of 5? Oh, there's one more factor of 5, so we could multiply this by 5, and that'll give us the correct exponent on the left-hand side. Well, whatever we do to the left-hand side, we have to do to the right-hand side. And if we multiply 5 times this, you see we're going to get 20x plus 5. How is that going to look like this? Somehow we have to show there's a factor of 4 involved. And while there's a factor of 4 in 20, there isn't a factor of 4 in 5. But we can use something we did once before when we did the quotient remainder theorem proof, and we broke something up in the third case. Why don't we rewrite this as 20x plus 4 plus 1. Now you can see these two terms have a factor of 4. Let's leave this side alone and factor out a 4 over here. Okay. Hey, now these things are starting to look the same. We have a y sitting here, and we have an expression in parentheses here. If we let y equal the expression in the parentheses, then 5 to the k plus 1 is equal to 4 times y minus 1, and that's what we were trying to get here. So we can just go from this step to this step, and then use the definition, and we're done. If you follow this pattern, you should be able to do the proof that is number 4 on the proofs sheet 2.